Okay, so let us continue. So, of course, you are seeing the definition of supremum and infimum officially here, but how do you define it right now? So, for example, I don't want you to look at the notes. So, if E is a subset of R, and then we say alpha is the supremum of E, if what happens? What was the English name for supremum? It was the smallest upper bound. So when you say it is the smallest upper bound, it means it has two properties. First of all, it is an upper bound. Secondly, it is the smallest. So exactly, so that you don't need to memorize anything as soon as you know what the supremum is in English. So if I want to prove alpha is the supremum of my set, I have two things to do. First of all, I have to convince myself that alpha is indeed an upper bound. So how can I prove that alpha is an upper bound? I have to convince myself that for all x in E, x is less than or equal to alpha. This is my first duty. If I want to prove this, I have to convince myself about this first. The secondly is that alpha is the smallest upper bound, meaning that if beta is another upper bound, alpha is less than that. Yes? Number two, if, what letter I have chosen? Yes, beta. So if beta is an upper bound of E, then what happens? Because this is supposed to be the smallest one, it means alpha should be less than or equal to beta. So remember this. If I want to prove a number, if I want to prove a real number is the supremum of my set, I have two things to do. First of all, I have to convince myself that alpha is an upper bound. How can I convince myself of that? By proving this statement. And this is not finished, because so far I have guaranteed that alpha is an upper bound, but I want more. I want to prove that this is the smallest upper bound. What does it mean? It means that if you give me any upper bound, beta, my upper bound alpha is at most beta. Yes, it is the smallest one. And then, for example, can you talk about, so gamma is infimum of E. How can I convince myself about gamma? Just a practice.
It's the same.
So one, I have to prove what?
It's the biggest.
For every x in E, yes, or I should prove what happens. X is greater than or equal to gamma. Or gamma is less than or equal to x. But this is not finished. Number two, I would say that if delta is an upper bound, is a lower bound of E, then can you complete it for me? I want to show that this is the greatest lower bound. If delta is a lower bound, what? Gamma?
It's bigger or equal to.
Bigger or equal to delta. Okay, so I was a little bit careless. So this one is for supremum. It's a little bit sloppy. I have written it carefully there. So supremum. And this one is for infimum. Yes. So you don't need to memorize. Okay? Just read it in English and then see what does it mean. Okay, and I have already mentioned that there is no guarantee that the supremum or infimum is within the set. But if you talk about minimum and maximum, it should be within the set itself. And we already did this exercise. You know why? Yes, we already did that, so we can skip this. Because the one that I have written here, E, n minus 1 over n belongs to n. Do you agree that's the same set? Because then n over n is 1, this is minus 1 over n. So we already did it. Okay? That's not something new.
Okay, but now this is something, a theorem. It's an extremely easy theorem, but I want you to remember it, because that is probably one of the most important theorems that we will use when we want to prove things regarding supremum. Okay. So let us try to understand what the theorem tells us. So theorem 119. So the theorem tells me that if E is a subset of R but not empty, okay, and it is bounded above, this is important, E is bounded above. Okay, then alpha becomes supremum of E if and only if this happens. For every beta less than alpha, there exists, what letter I have used, X in E, such that beta is strictly less than X, is less than or equal to alpha. Okay, so it seems strange, but let me tell you, it's extremely simple because I always forget and I visualize it and I find a theorem. So what does this tell me? So let us try to understand intuitively. So here I have the set R and I have a subset which is not empty and it is bounded above. For example, let us visualize it like this. Okay, and it continues forever from this side. For example, this is my E. Okay, can you point your finger to the supremum of this set? Where it should be? It's this hollow point. Do you agree? This is the supremum. Okay? This is the supremum of E. Does supremum of E in this case belong to my set? No, it does not belong to, because it's a hollow circle. Okay. But what does this tell me? It tells me that if I choose a number which is less than the supremum, yes, you see how trivial is that? If I choose a number which is less than my supremum, for example, here, then I can find an element in the set bigger than that. So that is what I have written here. Okay? So if alpha is the supremum and beta is a number which is guaranteed to be smaller than my supremum, I cannot at least find a number within my set which is larger than this beta. And of course, it cannot go beyond alpha because alpha is an upper bound. But it can be equal to alpha in the case that this is filled. It could be possible. Is that clear? Okay, so let us prove one in one direction. So the next one you can do it as an exercise. I just want you to see, this is because many of these things are very trivial, but you have to have a proof for them. So, how do you know that this is the case? So, for example, beta is less than alpha, and alpha is my supremum. Okay, so can you say, tell to me, the combination of these two statements tell something about beta. In other words, can beta be an upper bound? No, why?
Because alpha is the smallest upper.
Because alpha is the smallest upper bound, and beta is strictly less than alpha. So by these two, I can see that beta is not an upper bound. Of E. Do you agree?
alpha is the smallest upper bound, beta is less than alpha, so beta cannot be an upper bound. But if all beta is not an upper bound, what is the translation of this? When beta is not an upper bound? Yes?
There exists an x in E that is bigger than beta.
Yeah, that's the meaning. When you say it is not an upper bound, it means that when you were looking inside E, you found something greater than that. Yes? If you cannot find something greater than beta in your set, beta is already an upper bound. So it is nothing, it's just circular. It's not circular argument, but it is just repeating the definitions. So this means beta is not an upper bound of E, so this means there exists an x where in E such that beta is less than x. But on the other hand, this part of it is trivial because where is it? X is in E. What was alpha? Alpha was the an upper bound. Here, the smallest upper bound. Okay, so what does it mean? It means it is automatically less than alpha. It's just, it's very trivial, but it is very, very useful. So one part of it is actually very useful. If alpha is supremum of E, so let me write it here. So alpha is supremum of E, and beta is less than alpha, then the conclusion is that there exists an x in E. This side is very important. So beta is less than alpha, less than or equal to this. I want you to remember this. If you forget, visualize this picture. It immediately comes to your mind. Okay, let us make it a little bit more interesting. Do you think if I take this equality out, it is still true? Okay, so my question is that if everything is as before, if I give you that alpha is supremum of E and beta is less than alpha, can I guarantee the existence of an x in E such that beta is less than alpha, less than x, is strictly less than alpha? Because somehow that is very important in this course, because in this picture that I visualized for you, it seems that the answer is yes, if you imagine only this way of thinking. And then you have to expand your perspective here in analysis. Many things are counterintuitive by just very normal examples that comes to mind directly. But but they are not true unless you have a proof for them. So you see what I'm telling you is that, can I from here, these assumptions are there, can I go from here and just drop this equality sign? The answer is no, but try to find a counterexample. Can you give an example for me that if I take this equality off, the result becomes wrong? So it means that I have to keep the equality sign. Because you know, in this picture, it is very clear that there is something strictly less than alpha and beta. But in general, it cannot be true. Well, let me give you an example. For example, let me take E to be this set, union 3. Okay? So what is this set? If I want to give you a picture, this is R. So 1 is here, filled up to 2. So this is the set, 1 and 2, but it also includes one single point, a little bit there. Okay, so this is my set. These red ones in total is my set. Okay, but now if I ask you, by the way, if I ask you what is the maximum of E, let us practice. What is maximum of E? 3, because it is attained. It is in set and it is largest. What is the minimum? 1. Yes? What is supremum? 3. So this is what we need. Supremum is also 3. Why it is 3? Because first of all, it is an upper bound. Every element inside my set is less than or equal to 3, and I cannot go below 3. For example, why 2.5 is not? 2.5 works for all of them, but except 3. So 2.5. So 3 is the smallest upper bound. Okay, so supremum is, what is infimum? 1. Okay, so supremum. But now, do you agree that 2.5 is less than supremum? Yes? But can I conclude the existence of an x in the red part? Can I conclude that there exists x in E such that 2.5 is less than x, strictly less than 3? Alpha is 3 in this case. No, there is nothing. So you see that this equality needs to be there. So usually when you want to visualize, this is the first thing comes to mind. And when you have this in your head, you think that, okay, we can drop this equality as well. So this is the loophole in this course. Many things are counterintuitive, so you have to dig into it. If you don't have any proof for them, that you cannot rely on. Okay? Any questions here? Okay, so yes?
The red box, I think you swap places with alpha and x.
Oh, thank you very much. Thank you very much. I'm just reading. This x should be here, yes? Alpha should be. Thank you very much. Otherwise, so this is something I want you to remember. Okay, so now let us see what we have here. So this one is finished. We can go to the next one as well. So I went a little bit faster than I thought. Okay, so these are actually very simple ideas. Do you have any questions regarding these notations? You are already familiar with them in the calculus course, yes? So these are called intervals. Yes? Any questions regarding them? But there are two exceptions. There are two special cases I want to know. If you have this one, open interval from A to A, what is that? If I want to have an open interval from A to A, what is that? It is the set of x's in R which are strictly between A and A itself. Is there any numbers with that property? Nothing. So it becomes empty. So this interval is empty. But if I have this interval, this means the set of x's in R with which property A is less than or equal to x less than or equal to A. There is only one element with that property, and that is A itself. So these are special cases. Yes, and I think you can answer those things. So for an interval from A to B, what is the infimum? A. What is the supremum? B. What is the minimum? Does not exist. What is the maximum? Does not exist. But if I have this one, supremum B, minimum, supremum and maximum are both B, minimum and infimum are both A. Those are very simple. Any questions? Okay, so if you don't mind, let us. Okay, so now I want to start with an example here. The purpose is this. The purpose is to show that the set of rational numbers for analysis is not enough for us because it contains a lot of holes. Okay? You already know about this thing, yes? For example, because you know that if you compare the properties of the rational numbers and properties of the real numbers, more or less all the properties are being shared between them, except one important property that intuitively you can understand. If I draw the line, the set of real lines, if I want to stick to the rational numbers only, there are some points that are in R but not in Q. What is the most famous one? Pi, or a square root of 2. These are the numbers that are not rationals. So this means that I have to take them out, okay, when I am dealing, if I want to stick to Q. And that is bad because in analysis we want to do limiting process and we want to send my variable towards a number. And if there are some gaps here, this means that I have to jump from all those gaps in order to get closer and closer to the number that I want. So I want to have this continuum, yes? So this is the way, mathematicians, this is the most important thing that we don't have analysis on Q, we have analysis on R. Okay, so there is one axiom that we impose on R, which Q lacks. So this example is a very typical and famous example in analysis. We want to go through it because we have enough time now. So we want to show that this set, how it is defined. It is defined a set of all rational numbers such that they are positive, and when I square them, it becomes less than 2. Okay. You already know. If I, for example, if I just intuitively, if I ask you what is the supremum of this set? So this set are all rational numbers that are positive, but when I square them, it becomes less than 2. In other words, R is less than a square root of 2. So it means that if a square root of 2 is here, this set, and this is 0, this set contains all rational, positive rational numbers, but I am not allowed to go beyond the square root of 2. But if you, because you have already passed the calculus course, hopefully you know that I can get closer and closer to a square root of 2 even within the set of rational numbers. Yes? Okay, so then it means that your feeling might tell you that the supremum is a square root of 2. But then the problem is that the square root of 2 is not a rational number. So this means that if I want to work with Q, then this is not guaranteed that if I have a set bounded from above, it definitely has an supremum in Q. So my goal is to show that the claim is this: alpha B has no supremum in Q. Okay, so I want to prove this one in a way that analysis books they do, because it might be a little bit strange for you, because first of all, we don't have any proof why the supremum is the square root of 2. That is our intuition. And intuition is somehow good in this course. Sometimes it is counterproductive, so you have to be very careful. So I want to do it in a real way. We want to prove that B has no supremum in Q. Okay, if it has. Okay, so I would say that still we don't know if it, be careful, I am not claiming that it has a supremum. I am claiming that if there is a supremum for this B, that supremum cannot be in Q. That's my goal. So let alpha be the supremum of B. So let me write it like this. Let alpha be supremum of B, and to the contrary, assume that alpha belongs to Q. Okay. I want you to see this proof once. This is a typical analysis proof type. Okay, my question for you. You see again, I am not claiming this has a supremum. I am assuming that it has a supremum, but what I want to show is that if that supremum exists, it is not in Q. Okay? So I am assuming, let us assume to the contrary, that this is in Q. First of all, do you agree that alpha should be positive? Okay, why?
Because all numbers in there are positive.
All numbers there are positive. For example, 1 is there. Why? Because 1 is in Q, 1 is positive, and 1 squared is less than 2. So this is definitely true that 1 belongs to B. And alpha is a supremum. So definitely, so alpha is supremum of B. So what I can conclude from them, can you tell me?
It has to be bigger than 1.
Bigger or equal to 1. but 1 itself is positive. So this is clear, that this alpha belongs to Q. So let me write this. Alpha belongs to, alpha is positive because of this analysis. Okay, now consider alpha squared. Alpha squared can have three possibilities. Okay, one is that alpha squared is 2, alpha squared is less than 2, and or 3, alpha squared is greater than 2. Okay, but I want to show that none of them can happen. Okay, then it means that this assumption is wrong. Okay, we show that none of these can happen. And of course it means we are in trouble, yes? Because one of them should happen if alpha is in Q. So if alpha is in Q, either alpha squared is 2 or less than 2 or greater than 2. If none of them can happen, it means that this assumption is not correct. Okay, but one of them you can immediately rule out. Which one? Let's just say it. This one. Why? Because hopefully you have already seen that there is no rational number whose square is 2. So I just told it orally, okay? So we already know that this cannot happen. So 1 cannot happen. That's easy. I mean, based on what we learned before. Of course, the proof, I hope that you have seen the proof and you can reproduce the proof yourself at this level. But anyway, you know that there is no rational number whose square is 2. Okay, so now let us consider why the second scenario cannot happen. We show that alpha squared less than 2 gives rise to a contradiction. Okay? But I want you to feel what we are doing, because these proofs are technical in the analysis, but let us see intuitively what we can do. So let us imagine that 2 is here. I am assuming that alpha squared is less than 2, so alpha squared is somewhere here. Okay? And where is alpha? Alpha is probably here, and if I take a square root of 2, it's here. So I'm just trying to visualize it. I am not respecting the scales, okay? So, my claim is that if alpha is in Q positive, we already know that. I want to prove that there exists, so claim, there exists an epsilon in Q positive such that x plus that epsilon squared, alpha plus epsilon squared is less than 2. This claim, intuitively, it is very clear. I want to wait a little bit for you so that you can digest it. So this picture, you know that in part 2, I am assuming alpha squared is less than 2, and I want to show you that it gives rise to a contradiction. And then I will do the same thing and show you that this will also give rise to contradiction, and none of them can happen. So it means alpha cannot be a rational number because all of it is coming from being rational. But now I am working on this part now. On this part, this is the picture that you have in mind. 2 is somewhere. Alpha squared is less than 2. And for making it easier to understand, I have put alpha and square root of 2 somewhere here. I am not claiming that I am into scale. Scaling is not good. But first of all, can you feel what I am saying here? I am saying that there is an epsilon of a positive rational number, a positive rational number, so that when I add that to alpha, and square it, it is still less than 2. This is extremely trivial, I mean, from intuitive point of view. Do you see why? Because it is very clear, you know. So for example, if I choose alpha plus epsilon here, it is very clear that this will go somewhere there, you know. Alpha plus epsilon squared will be somewhere here. Okay? But here you have to, in analysis, you have to really prove these things because we are not working with square root of 2's and anything yet. Okay, so how can I prove this? In other words, if I want to claim such an epsilon exists, I have to offer that epsilon. I cannot say that, okay, feel that it exists. Yes, it exists, but I have to offer that epsilon to you. Okay, I have to offer a positive rational epsilon for you so that under this condition, it guarantees this one. Okay, for example, alpha plus epsilon squared can be written as alpha squared plus 2 epsilon alpha plus epsilon squared. Yes, do you agree? It is very clear, you see that. Do you agree that I can choose epsilon to be a very, very positive rational, a very small positive rational number? If epsilon is a very, very small number, then more or less alpha squared will dominate. Do you agree? And then it means that in principle, I can make sure that this can be made smaller than 2. Why? Because this one itself is less than 2, but there is a room between 2 and alpha squared, this room. By choosing epsilon, a very small number, I can make this distance, this number smaller than this distance, so that it gives me the safe zone to be still less than 2. Is that clear? Okay. Okay. But if you are convinced with this, tell me where the contradiction comes from, then I can go back and make it a little bit technical to really offer you the epsilon in an intuitive way. Why do you think if this claim is proven to you, then the contradiction arises? Okay, might be I confused. Okay, let me just explain again. For the time being, by this picture, is it clear that this should be true at least? Yes? Do you agree with this one? Okay. So let us, for the time being, imagine that we prove the claim. Okay? And we have this. Okay? But I want you to tell me why this gives rise to a contradiction. Yes?
Because you can always rewrite alpha plus epsilon as a rational number, and that can become the new.
No, in contradiction with what? You know, so you see, what I'm saying is that forget about these things. Imagine that we prove this, so we can rely on it. But I want to tell me where the contradiction arises from. Yes?
Isn't alpha the largest upper bound?
Yes. So can you make it precise? So it means that alpha plus epsilon
Will be greater than alpha.
Alpha. Why? Because epsilon is positive. But why this is a contradiction?
Because alpha is the
Supremum.
supremum.
No, it is not contradiction yet. You are right. This is the contradiction. But why it is contradiction? Because if a number is greater than supremum by itself, it is not a contradiction unless I can prove to you what?
That it's still less than 2.
No, it is. Oh, you see, alpha plus epsilon is greater than alpha. By itself is not a contradiction. Do you agree? Because alpha plus epsilon is indeed greater than alpha because epsilon is positive. But if you combine this fact with some other fact we know, then the contradiction shows itself. Yes?
Alpha plus epsilon is in B.
This is crucial. So you have to show that alpha plus epsilon is in B. On the other hand, alpha plus epsilon is greater than its supremum. This then becomes contradiction. Do you agree with that? So this by itself is not a contradiction because this is indeed true. But the contradiction is that, so how can I prove that alpha plus epsilon is in B? Yes?
You can rewrite it as quotient.
No, we don't know yet. And we don't need that. This is very good in analysis. So don't think about, you see, if you want to enter this country, you have to have three conditions. You should belong to Q, it should be positive, and its square should be less than 2. Does alpha plus epsilon fulfill all these conditions? Yes. Why is that? Alpha was what type? Alpha was in Q. Epsilon is in Q. So what I can conclude that alpha plus epsilon is in Q. Do you agree? Yes. So by the way, alpha was Q plus. This one is also Q plus. So this one also will be Q plus. Okay. So it is in Q and it is positive. So this is guaranteed for alpha plus epsilon. This is guaranteed. And moreover, what is guaranteed? And alpha plus epsilon to the power of 2 is also less than 2. So this alpha plus epsilon respects all those three conditions. So then it goes into B. So this from here you can conclude that alpha plus epsilon goes to B. This is no contradiction. Yes? Because alpha plus epsilon is in B and alpha is the supremum of B. So this means that I have to agree that alpha plus epsilon is less than or equal to alpha, which is contradiction now. This means that epsilon should be less than or equal to 0, and that is my contradiction. Is that clear? Okay, so let me just jump because I don't want to confuse you because this is important. That's one technical. You need more experience to come up with the correct construction for epsilon. But everyone understands what I said? Okay, so let us jump to the next one, and then if we have time, we can come back to the other one as well. So number 3. So I want to show that we show that. Of course, by the way, I have written all the details in the notes. If some interested to see in a correct way, you can read the notes. So we show that alpha squared greater than 2 gives rise to a contradiction as well. A contradiction. So now what do I have if I want to understand it? So can you help me now? So alpha squared this time is here, 2 is here. So if I want to visualize square root of 2 is here, alpha is here. But I know that alpha squared this time is greater than 2. So can you more or less, can you write a claim here for me? Based on your intuition that based on experience you got from this one? Because I ask you, this is intuitively very clear. Can you write something analog to this, to that case, as a claim? For the time being, we accept it as your claim. I mean, if you want, we can prove it later. So, claim. I start with something. There exists delta in Q positive such that I'm waiting for it. So imagine. So what should I write? Alpha minus alpha minus delta squared
Bigger than 2.
bigger than 2. Yes? I mean, intuitively it is very clear, yes? Because it means that alpha squared takes me exactly here. Square root of 2 after squared, it takes me here. Of course, if I go a little bit lower, then I will end up somewhere here, which is greater than 2. Yes? Intuitively, it is very clear. So again, let us accept this claim. Okay? But can you help me to reach to a contradiction now? So let me. So let us say that this is proven for the time being. Okay. We claim another claim. Alpha minus delta is an upper bound of B. So I claim something. Based on your intuition, for the time being, we accept it. But I want to claim another thing, and I am claiming that alpha minus delta is still an upper bound of beta of B. Do you agree that this is also another contradiction?
Yes.
Because if I can show this claim is true, it is in contradiction with what? Alpha being the smallest one. Because I could find something smaller to be still an upper bound. Do you see that if I can prove this claim, then I have my contradiction? Is that clear for everyone? Is that clear? Okay. So how can I prove that? I prove that alpha minus beta is an upper bound. So this is a very technical theorem. Let us say it is not. Okay? Assuming contrary that, to the contrary, assume that alpha minus delta is not an upper bound. Of B. Then, can you complete this sentence for me? To the contrary, assume that alpha minus delta is not an upper bound of B, then what happens? There exists what? An R where in B such that what happens?
Alpha minus beta.
R is greater than alpha minus. Yes. Is that right? That's the consequence. Okay, but then what? Why this is a contradiction? Then R squared becomes greater than a alpha minus delta squared. But there is some small thing that I have to make sure that I can choose delta so small that alpha minus delta is still positive. Because then I will have trouble here. Okay? So, then what happens, but this one itself is greater than 2. Okay, so then what does it mean? Yes?
Means that R squared is greater than 2.
Means, therefore,
It's a contradiction because R is in B.
R is in B, yes? Because this means that R is not in B. Yes? Because to be in B, R squared should be less than 2. So we have to accept that on the one hand, R is in B, on the other hand, R is not in B. And that's your contradiction. It's a little bit convoluted theorem, you know? So you have to prove two things, you know? And then within this one, you have to use proof by contradiction. Okay. So I have written this very clearly in the notes. So if you, but of course we don't have time for it now. So I have also constructed this epsilon that I claimed its existence, and it is trivial to imagine it, and also constructed this delta for it. Okay. And by the way, I don't think that I could do it the first time I saw this analysis course. So, but I want you to read and understand it. As soon as you understand it, that's okay. But coming up with the correct form, constructing the correct forms of these claims would be extremely hard. Okay? Any questions? Understandable? So I will write the reading sections. So if you just follow the reading sections, you will not be behind. And again, as if you are comfortable with the homework problems, you are really on the safe side. Okay? Any questions? Thank you. One